Now that we know how to find the B field for a few different situations, we can start applying these ideas to a variety of problems. For example, we now know a current carrying wire causes a B field, and we already knew that a B field exerts a force on a current. In that case, there should be a force between two parallel current carrying wires. We'll say they're carrying currents I1 and I2, both to the right, and they're a distance little d apart. What will their magnetic fields look like, and then what will that cause in the way of forces between them? First, let's look at I1, which is red. Everything in red is related to I1. If we look at the direction of the B field, you point your right thumb to the right, and you'll see your fingers come out of the board or out of the page, curl around, and go back into it down here. So everything above is out of the page, everything below is into the page. Now we know what the B field from wire number 1 is. We can look at the B field from wire number 2. This is green. Again, it's going the same way, so your fingers will curl the same way. Everything above wire I2 here, the field is out of the page. Everything below it, it's into the page. Now, the force on current I1 caused by the green magnetic field is going to be, we can write it as F of 2 on 1, is I1 L B2. And we also have to multiply by sine of theta. This is the angle between the B field, which is into or out of the page, and the current, left or right. That's 90 degrees, so the sine theta part equals 1. Now, if these wires are supposed to be infinitely long and there's any force at all between them, we know if we add it all up, we're going to get an infinite force, and again, that's not useful to us. We usually do this problem by finding the force per length. We divide by L on both sides, and we could say the force per length in this case is I1 times B2. We just figured out how to find B2, though. Our first equation here, we need to do mu naught times its current divided by 2 pi times the distance between them. So we have our current I1 that's being acted on, and then mu naught I2 over 2 pi d. So our force per unit length can be written like this: mu naught I1 I2 over 2 pi d. What's the direction of the force? Here we have to study this figure carefully. If we look at this, the B2 field is coming out of the page. I1 is going to the right. So you have to take the fingers of your right hand, point them to the right, and then curl them out of the screen or out of the page. If you do this, you'll notice your thumb points down. So this I1 is being pulled down towards I2. What about the force of 1 on 2? We use the same logic. We look at the current I2 multiplied by the magnetic field from B1. The field from B1, same as we would have gotten up here, only we replace the current I2 with I1. We get the same answer here, mu naught I1 I2 over 2 pi d. Now what about the direction? B1, this magnetic field, is into the page everywhere along I2. So now you point your fingers to the right and curl them into the page, and when you do that, your thumb points up. So what we see is the bottom wire is pulled towards the top wire. Now really, we didn't have to do all this work to see that these forces were equal and oppositely directed, because that's what we would have gotten from Newton's third law. For the first time, we see things that are alike are attracted. We haven't seen this with magnetic poles, we haven't seen this with electric charges, but we see it with currents. What about if we have things in opposite directions? So we leave current I1 moving to the right, current I2 now moves to the left. The magnetic field from I1 stays like it was, but now the magnetic field from I2 goes into the page up here above and out of the page below. Now let's do the right-hand rule for the force on current I1. You point your fingers to the right, curl them into the board, and your thumb points up. So it's pushing away from the other wire. We do the same thing at the lower wire. You look at the current for I2, point your fingers to the left, curl them into the board for B1, and your thumb points down. So opposite currents repel, but like currents attract. How strong is the force? Well, we can do a little math here. Let's say we're jump starting a car again. We say the jumper cables are carrying 400 amps of current down one side and back up the other. Let's assume the separation of those two wires is 2 centimeters and look at the force of repulsion per unit length. So we've got our constant mu naught. We've got I1 and I2, they're the same, 400, divided by 2 pi d, which is 0.02 meters. We get an answer of 1.6 newtons per meter. How big of a force is this? Well, if our jumper cables are 4-gauge copper wire, they will weigh about 3.7 newtons per meter. So this isn't really a particularly large force, even when we're talking about very big currents, really pretty close together.